Hello and welcome everyone to this webinar hosted by UReason. My name is Jules Utmans. I'm presenting to you today. I have a background in AI starting in the 90s, and I've been involved many times in the past 25 years in prognostic and predictive programs that ensure asset integrity for critical assets and critical processes. Here are my contact details. If you have any questions after the webinar, don't hesitate to email me. I work at UReason. UReason is a software company that provides software for real-time condition-based and predictive maintenance. And I help our customers on a daily basis analyzing process data and asset upsets and helping them to turn this data into value in our software. At UReason, we combine our domain expertise and software knowledge with our customers, and we help them from the data to solutions. We have offices in Rotterdam, which we see here in the picture in the top right, and in Reading in the UK. Our customers are predominantly manufacturing and process-related customers, which are located in Western Europe and the Northern Americas. UReason is active in the area of real-time condition and predictive and prescriptive maintenance. Our field of operation is from helping customers to insights into data, to helping asset owners, OEMs, and MROs with data-driven maintenance solutions. Our software, APM Studio, is used at different levels in the automation pyramid. Embedded with OEMs, monitoring faults and risks in isolation to the asset, and an asset can be instrumentation, an actuator, a pump, a compressor, a filter, etc. But we also work at level 1 and level 2 in the automation period, where APM Studio is used to monitor faults in relationship to a process. And when our software is deployed at level 4, APM is typically used for optimizing the maintenance cost and the planning associated to an asset base, supporting a process, of course. Today in this webinar, we will have a look at how you can use streaming data from your assets and use this to optimize process availability, detect issues early, and improve asset integrity. We will first discuss why you want to use this data before going into detail as to what data we need and where to get this data from. And towards the end of the webinar, I will provide a demo. And of course, there's also time for Q&A, as Saika already indicated. But be aware, I will also ask you some questions during this webinar. So asset data holds information, or the information that allows you to improve your total cost of ownership and increase your asset availability. It further allows you to reduce your service losses and, as important, the risk of operation and unexpected downtime that influences your production plans. The asset data also holds value that allows you to recover revenue and reduce the amount of planned maintenance. But where and how do you start to unlock the value from this data? Do you need access to streaming data at the lower levels of your automation systems? Or can you utilize the streaming data stored in process historians? Let me ask you a question to start with. Have you started, or do you want to start using data from your assets to prevent asset outages and process outages? So what will happen now is you will see an interaction appearing in your screen where you can provide an answer to this question from me. So you can answer with, I've started to already use data from my assets, or I've started and need some assistance, or I want to start, but I don't know where or how to start best. Let me just wait for you to answer the questions. So most of you, thank you for answering, by the way. Most of you have already started using the data. Actually, it's going to a tie now. Some of you have started and some of you have not started. It's a tie at the moment. And some of you want to start but do not know where to start best. Okay, thank you for your inputs. So, process data holds valuable information on how your assets are used by operations. The data from the devices and I/O out in the field is communicated to your automation and control layers using different protocols. The protocols depend somewhat on the age of your installation and are often driven by company general practices as to what may be used. So the devices out in your field may talk 4 to 20 milliamp with hard superimposed over it, or they may provide some more modern interfaces like Modbus and Profibus before the streaming data actually ends up in your SCADA and DCS systems. These are just some examples of systems and sensors, of course. Now, in addition to process data, hard and bus systems such as Fieldbus and Profibus also hold a lot of valuable data and diagnostic data about your actuators and instrumentation out in the field. Um, some, but not all of this data is used by your SCADA or DCS control systems to support operations. The process data collected at level 2 is most of the time stored in process or data historians at level 3 for future uses. And we see some examples here. Again, it's not a complete picture, but typical process historians that we encounter are Pi from OCSoft, IP21 from Mesmentech, the Wonderware historian from Schneider, and some others as well, Honeywell PhD. But to prevent outages, in addition to the process data, you also need access to records of work orders, inspection results, preventive, corrective maintenance activities from your CMMS systems and inspection systems that are typically at level 4 in the automation period. Next to this, so next to the process data and the data from your CMMS systems, you also need access to failure data, but this is often not stored in a standard way. So there are few or very little vendors that also provide you with databases to store failure information in. So the data from the different sources at both the OT and the IT levels is required to prevent outages on your assets and to improve the asset uptime and reliability. Very often I get the question from customers that they need access to high frequency data, high frequency streaming data. But in most cases, real high frequency data is not required except for real-time condition monitoring systems on, for example, critical rotating equipment, where you need to perform frequency analysis on acceleration or vibration sensors. Now, let me ask you another question in the session here. What data do you currently use to analyze or prevent outages? And this should be a multiple choice. So you may be using data from sensors directly, or you may be using data from process historians, which provide sometimes aggregated data, or you may use the diagnostic data from instruments and actuators that is communicated via the bus systems or hard, or data from maintenance management system. And of course, there may be other sources as well. So I'll just wait for your answers to come in. So the majority actually, and this is changing again while I'm trying to provide the summary, it's actually a tie between all the 5 answers except data from maintenance management systems. So you are using data from sensors directly, data from process historians. The tie situation actually changed just now. You're using diagnostic data from instruments and actuators, so diagnostic data from asset management systems that collect hard, field bus, or bus related diagnostic information. So it's a variety, quite a variety of different information sources. Some of them streaming, some of them can be queried upon request. Thank you again for answering those questions. So we'll have a look at what is needed to cross the chasm between your data collection, be it streaming or be it from a process historian, and the analysis environment where data scientists may search for insights in your data, and the production environment where the streaming data in combination with, for example, deployed machine learning models can be used to prevent unwanted downtime or improve asset integrity. So the world of data scientists is where the data is analyzed to gain insights. Different analysis models are tried and tested to see if you can predict a certain failure or degradation on your assets or process and determine the remaining useful lifetime such that you can optimize the planning and prevent unwanted outages. Once a model has been developed by your data scientist or your analyst, you want to deploy it. So if the model that has been developed has good results, for example, an accuracy of prediction failure above 80%, you want to use that result in your live environment such that it provides insights to production operations and asset management on a 24/7 basis. What we at UReason typically do is we use a common standard that has been out there for uh, quite a few years, over a decade, called PMML, Predictive Model Markup Language. And this is a method, it's a standard to deploy machine learning models onto live streaming data. So typically when you access data from historians or streaming data, you have some reasons. Sometimes you may want to do undirected searches to explore the data sets to find patterns of interest. But you probably do this when there's when you are a frequent user of the data set. Directed search is the most common usage. So you're looking for something specific in the data set, a process upset that happened, energy consumption that increased, etc. And when you're doing directed searches, we typically apply a method called CRISP-DM, of which you see the picture here in the overview. And this method provides a structured approach to analyzing the data geared towards a result that you can put online. So it starts with understanding the business, understanding the process, understanding the asset that the data or the process that the data is collected for, doing data preparations. And sometimes when doing the data preparations, you have to go back and forth, and sometimes you do some data synthesizing to add additional data columns, data streams to it. Once you've gone through this first three steps, you typically, if you're training a model to detect a certain failure or calculate a remaining useful lifetime, you start filtering out the data that is of value to the specific class of failure that you want to predict. And this is called feature selection. So the first four steps are quite iterative, as well as the next four steps. These are quite iterative as well, because once you have drilled down on the features that allow you to classify a certain failure and determine the remaining useful lifetime, you start model training and model validation, which has a number of iterations before you can go to model deployment. And especially in the first three phases and the last three phases, there is typically, and this is talking from the UReason perspective, a heavy end user involvement because it's knowledge intensive. And there are certain things hidden in the data or not stored in the data, but available to you as expertise and skills because you've been working with these assets or processes for a longer period of time. So if you want to go, so the analysis is typically done with tools such as Python, R, SPSS, RapidMiner, KNIME. There's quite a large variety of tools, and later on I'll show a small demo inside KNIME also of how this analysis can be done and how you can get to a PMML file. And once you are happy with the results, so once you are happy with, for example, a classification model that predicts a certain failure above a certain percentage, above 80% certainty, you want to use that model online for production and for your maintenance department 24/7. And PMML, as I indicated earlier, is a very nice standard to be able to do this and to stay vendor independent. Within our software, APM Studio, we have a PMML reader that can also understand the models that have been trained in your analysis environments, be it SPSS, SAS, NIME, etc. And they can be run linked to the streaming data inside APM Studio. So let's have a look at an example. I have data and functional degradation data from various process equipment in my plant. And this functional degradation data was, of course, streaming. This is a snapshot from history from a process historian. And I also have functional degradation data from my CMMS system, i.e. I know when certain of my valves, my coolers, my pumps, etc. have shown certain issues. So I have all the ingredients to start a predictive maintenance program. So looking at the process data, I do not see a clear relationship between the various pressures, temperatures, and flows that are measured. I can see some spikes, I can see an upward and a downward trend, but I see no clear relationships. However, when I look at the data in relationship to the failures that have been recorded, which we see here on the right-hand side, so we have the data here in these columns for pressure, temperature sensors, some flow sensors, the velocity of a pump, and here in the bottom I have a number of additional data sets that I added for my cooler condition, which tells me about the condition, the health condition of my cooler, my valve condition, identical, if there is an internal pump leakage, if I have hydraulic accumulation, and if the process was actually in a stable condition. And when we look at this table, I can see that, and this is just a simple correlation matrix on this raw data, I can see that there is a clear relationship between the cooler condition and my input data, because I have strong negative and positive correlations. However, I can see that there is no strong relationships yet, but I can get these from the data as well, between the valve condition, internal pump leakage, etc., and the rest of my process data. But that's one of the things, one of the creative things of the data science, is to figure out what these other relationships are. So using the process data allows you to provide early detection of fouling of an asset or asset degradation, so you can prevent upsets. But to do this, I have to synthesize data from multiple sources so that I can train and validate such a degradation model. Um, I find that this is not done often because there are silos of data access in organizations. Remember that on a few slides ago, we discussed the ingredients, the streaming data, historical data, but also the diagnostic data from hard and bus systems, and the maintenance data from CMMS systems and inspection data. All of that needs to be synthesized together in order to create valuable insights that would allow us to detect potential failures, early warnings, such that we can prevent the actual failure from happening. And we, based on the PF interval, the time that you have to respond, um, allowing you or your organization to have a suitable time window in which you can still react to the disturbance. So let's have a look at a close look at the data and see if there are relationships between the process data and the wear and tear of my equipment that I showed on the previous slide, the pumps, the valves, and the coolers. So you should see I'm sharing my analysis environment. This is the environment which is called NIME. NIME is one of the open source, freely available environments. It also has a subscription model, of course. In here, I have tons of utilities to access read I/O from different sources and write I/O to different sources, to do data manipulation at the column level, row level, to create different types of views, graphs, etc. on my data, but also to do different types of analytics. So for example, I can drag and drop a neural network from the palette onto this scheme. And by doing so, I have the capabilities available of a neural network, which I can then configure once I've connected it up. So let me first show you the data. So this part of my workflow is really extracting and transforming the data that I receive, because I have pressure data at a different frequency that I have, for example, my flow data, and my cooler data again is at a different frequency. So what I've done here, I've done a number of data manipulations where based on the data that is available, I've basically extracted, transformed the data in such a way that it is all in the same time domain. Once this is all done, let's have a look at this data set here. I have a data set of well over 13 million rows, in which I have all the pressures, temperatures, but also the conditions of my cooler, the valve, which are numeric values here, represented such that I can start analyzing it and doing training models with it and validating it. So the first thing to do is to have a look at the correlation that we have in the data set. So this is just a simple Pearson correlation matrix, and it provides us with an overview of positive and negative correlation and its values. You see, when I hover over these fields, I can actually see the actual correlation value between my different process inputs and the different labels that I added to the data set for the cooler condition, valve condition, etc. And this provided me with the insight that the cooler condition can very likely be either determined by using deterministic rules on the pressures and the temperatures, or can be determined easily by training, for example, a model to recognize this specific condition. So the number of blocks I have here, there's some filtering done here again, are here to instruct the system to train a neural network, and this block is there to validate a neural network. And the results in the confusion matrix, if we look at these, of this exercise training the neural network, are quite positive. I have 3 cooler conditions, 100% okay, going towards failure, and failure is imminent. These are the 3 numerical values that are represented here. And in this confusion matrix, we see the actual scoring of the classes that were provided to the algorithm, to the neural network in this case, and the unseen data. And we see that we can get quite a good prediction capability of overall 98.48%, which is very high. There's still some false positives where the predicted class, for example, here in 43,000 of the cases is near failure, where it should actually have been failure. So it should actually have been over here, but that's a matter of tuning, not overfitting. The other block that we see here is that there's this PMML writer. The PMML writer actually exports the results, i.e. the algorithms that have been configured in this neural network block, as a PMML 4.0 compliant model, which I can then use in a remote location like APM Studio to link it to the actual streaming data. So let me return to the presentation. This is just a catch-up that you have it in slides as well. I set up an analysis workflow inside KNIME, and in this analysis workflow, apart from the transformation of the data, I also trained and validated a neural network that provides me with a pretty good set of results that are worthwhile deploying inside APM. So the next step actually is, when I have the exported machine learning model, I would like to link it to the streaming data. I've trained the model, validated the model on data that it had not seen. And the next thing now is that I would like to link it to a model inside APM such that I can inform operations and maintenance on the upcoming upsets of the cooler condition in this case. So I'm moving in here, APM Studio. So this is just a dashboard for my system, in this case, one of the pumps in my system, showing the efficiency of the pump and where it's currently at on the performance curve, and showing what the total dynamic head is. There's some kind of recipe being run here, so it's quite periodic, you could say. And it also provides me with an insight of the highest Namur alarm state and the total number of alarms that I have incoming. Inside APM Studio, you can connect APM Studio to live streaming data sources, but also to offline data sources and to databases that contain transactional data. So in here, I have a number of data sources set up. So let's have a look at the cooler data. I have temperatures and pressures and the cooler efficiency all available to me here inside APM. And over time, we can see the points incoming here. Over time, this data is changing, but it's changing very, very slowly. I've set up a set of classes inside APM. So there's some built-in classes, smart classes as we call them, and smart objects that provide you with capabilities, for example, as we saw earlier for the pump, that based on the speed, suction and discharge pressure and the flow, it will do a lot of calculations embedded to determine the net positive suction head, the efficiency, the total dynamic head, etc., which can then be used inside your application, inside your rules, to detect certain dysfunctions. These equipment classes are like blueprints for objects. So here we see a number of objects. They do not have a fancy representation. This, for example, is one of the pressure transmitters. Here is my cooler, for example, and I can see, the current alarms that are active on the cooler. I can see what current data is coming into my cooler. I can see that the model is predicting it is currently failing. And let's have a look at how it's doing that. So apart from the model, I can define alarms. I can have KPIs and KPI calculations. But let's have a look at how the system APM Studio is actually linked to this machine learning model that was trained on recognizing a certain class of failure on my cooler. So in here, this is a processing rule. Processing rule was created like everything inside APM in a graphical manner. So we have a set of palettes depending on what type of editor, what type of focus you're in. So if you're in a state model or in a class model or in processing or in both types, you have different elements on the palette that allow you to construct these reasoning schemes. And this scheme actually takes the cooler and then runs the ML model based on the data that is being mapped to the cooler. So we saw earlier on in the model, there's a number of data points mapped to the cooler. And based on that, the ML model, which is inside this block, is run, and then it's looped continuously. So it's continuously 24/7 checking that the cooler condition is in a certain mode, such that I can notify and inform maintenance and operations about the dysfunction that we want to prevent. So here we see a PMML block, which is one of the blocks that you can just drag and drop like this from the palette and then configure. So the PMML model here has actually been configured to read my model.pmml, which is the export here of my PMML writer. So this PMML writer in this workflow, actually when the neural network is trained and validated, contains the configuration of my neural net as a PMML compliant file, which tells it about, because this is a neural network, the amount of neurons, the amount of hidden layers, and the different weights of the neurons in my neural network, and my optimization method that I use, etc. So it's a very simple way of going from an analysis environment to deploying machine learning models in real time. But you can, of course, also combine this with Outages to provide you with insights on upcoming incidents that are related to process upsets or asset upsets that you want to prevent. So here we see a probabilistic risk model for pump cavitation that has a number of tests for high discharge pressure, which can be deterministic if then else tests, high discharge pressure, low suction pressure, etc., but also bearing failures, which can be frequency based. So they can be tests that you perform on a frequency domain received from, for example, an acceleration or vibration sensor. All of this comes together inside a dashboard, and this dashboard, as I already showed, is completely web-based. And again, here the dashboards inside APM Studio are quite user-friendly. The setup, it's a low-coding environment, so the entire setup of the system is relatively straightforward. It drives on the class definitions and the objects that you have available inside your domain, inside your APM Studio domain, which is linked to the data sources that are available. Okay, let's go. I'm looking at the time. I'm running a little bit late. Sorry about that. Let me ask you another question. Are you planning or do you want to reduce unplanned outages on your assets? So let me select the question here and start it again. So you should see a new question popping up in your screen. Do you want to reduce unplanned outages on your assets with a number of answers? I do, and I have a solution. You already have something in place to take care of this. I do, but I'm looking how to, or it may not be relevant to you at this point in time, or you don't have a solution in place at the moment. And I'll wait again for your answers. So most of you are interested to reduce unplanned outages on your assets. That's kind of logical because it was also the title of this webinar. But you're looking how to. You're still orienting on what is the best method, the best feasible method. Now I think with APM Studio and the analysis environment that you may have already chosen, R, Python, SPSS, RapidMine, or other environments, APM Studio can provide you with a means to monitor assets 24/7 on streaming data, but also on data that is collected in transactional databases like CMMS systems. If you have insufficient failure and/or functional degradation data, you can also start with APM Studio with just visualizing the data and then doing condition monitoring program, and you can extend this slowly into a predictive maintenance program. You don't have to start, of course, with predictive maintenance. The demo that I showed shows how you can link up streaming data sources and how you can combine data from multiple sources, streaming and transactional, to prevent asset outages. I hope that this webinar was valuable to you, and we have come to the end of the webinar, but to the start of the Q&A session. So I would like to start with thanking you for participating in this webinar. If you do not have time to stay for the Q&A, and if you do have questions, let's go. I mean, let me check with Saika and Carlos if there's any questions from the audience. Okay, there's a number of them. Thanks, Carlos, for summarizing these. Okay, the first one is, what interfaces does APM Studio provide for streaming data? So we have a number of interfaces for streaming data. So OPC, DA, and UA is one of the sources for streaming data, as well as, for example, MQTT. But it really depends a little bit on your setup. So if you're an asset owner, you may already have streaming data available at your level 2 layer in the automation system, so at the SCADA DCS level in OPC or via MQTT servers. But it may also be the case that you do not want access to of other programs to the level 2 system. So you may have a process historian which is collecting and storing data typically on a second basis at level 3, where we can also tap into. So streaming data does not have to come from the lower levels of the automation period. It can also come from a higher level, such as a level 3 where a process historian resides. Streaming data may also come, I just mentioned the level 2, level 3 interfaces like MQTT and OpenCDA, but streaming data may also come from lower levels, from a serial port to which we have interfaces, or from IO link, or in certain cases, but we typically do that for OEMs, typically from the 4 to 20 milliamp interfaces that are available. I hope that answers the question. Okay, the second question is, can I deploy APM Studio at the DCS SCADA level? With some more details, I have data available in an OpenC server. Oh, so yes, you can deploy, as I just indicated, APM Studio at the DCS and SCADA level. But in certain cases, third-party or other application software is not allowed at the level 2 automation layer. And then if you have data available in your OpenC server and it's also streamed to an historian, you can also connect to it at level 3. The next question is, when I use APM at the device level, what are the typical interfaces to get real-time data in? Yeah, so at the device level, we have a number of OEMs where internally in the device, MQTT brokers are being used to communicate and provide a publish and subscribe mechanism to I/O from the device internally to the device. So MQTT and MQTT Spark plug is something that we see very often, and instead of all kinds of proprietary protocols. But proprietary protocols are also something that we support. Of course, those are custom interfaces, and yeah, in the case of custom interfaces, we always need some investigation to see how we can make that into a module inside APM Studio. So we did May of this year, I think it was in May of this year, we did for one of our customers some custom interfaces to Advantech IO modules that provided a very specific way of communicating their data at the lower level. So this is at level 0, level 1, roughly in the automation period. And next question is, are there limitations on the amount and the frequency of data I can get into APM Studio? That's a good question. So there are no limitations on the amount of I/O that you can get into APM Studio. However, the amount of I/O that you get into APM Studio is limited by the license. So we have I/O-based licenses. And it's also somewhat limited by the platform that you run on. So if you run on chip, which we do embedded on an NXP or an ARM chip, the amount of data that an APM instance can digest, process, and turn into meaningful insights is of course limited, because the compute power on those chips is somewhat limited. It's quite strong, but somewhat limited. So typical I/O amounts on chip are up to 1000 roughly. And of course, if you deploy at level 2 or level 3 in the automation pyramid, then there's more processing power capability available, and there's no real limit. You can cluster APM Studio to fulfill your needs, and there's no real physical limit as such. Now, when it comes to frequency, this is something that is also of importance. It's not only the amount of I/O, but also the frequency, especially from rotating equipment, from vibration, acceleration sensors. You get high frequency data at 20 kilohertz or 10 kilohertz, depending on the type of application. And sometimes these sensors already provide a certain level of aggregated information. So I'm actually currently evaluating a acceleration sensor from a German manufacturer, which does a lot of onboard processing inside the sensor and provides RMS values, etc., in a profile to subscribers via IO link, which is quite powerful. If you provide high frequency data to APM, again, it depends on the amount of compute resources that you link to it. So you need, in order to evaluate high frequency data, also at a high frequency to do frequency analysis, etc. You need sufficient compute power, but yeah, most of the servers nowadays and most of the cloud services also nowadays have sufficient of that available. There's another question: what machine learning algorithms are supported by APM Studio? So in addition, I mean, I showed PMML, we have fuzzy, but PMML basically supports Bayesian networks, support vector machines, naive Bayes, neural networks, FDA, LDA, different types of trees, decision trees. It is quite extensive. I think in total PMML supports about 25, I think, or 21 different algorithms, or algorithm types, I should say, and different subvariants, but also the pre-processing, etc., that you apply to it. Now, in addition to that, APM Studio can also support less common machine learning algorithms, or the machine learning algorithms that you find in Weka, for example. So it's quite extensive. I would say we have support for 8 out of 10 of the algorithms that are out there. Okay, let me have a look at Carlos. Carlos, are there any more questions? No, no more questions. Carlos is typing back to me on the internal presenter chat. Okay, so that brings us to the end of the webinar. Again, thank you for participating in this webinar. And if there's any questions, you can contact me on my mail address. All the participants will also receive a PDF of the presentation and a link, I believe, to rerun the webinar and to watch it again at a later point in time. Again, thank you very much for participating, and I hope to see you soon again. Bye-bye.